Good morning, Sudhir. I'm going to go ahead and correct your homework assignment number 2, your multiple regression. Okay, this is the one about the zombies. So question 1 is, what are the IVs and the DVs? The IVs are the stages of zombieism and the number of days outside the safety zone. That is correct. The DV is how many days they have left of being human. That is their DV. That is correct, is 2. So number 2, what is the sample size? And is it large enough to satisfy the statistical power? So you put down the sample size is 250. That part is correct, but you did not tell me if that is a large enough sample size or not. So I'm going to switch you over to our Moodle that explains sample size. Hold on. And here it is, sample size for multiple regression. And a good rule of thumb is you want a minimum of 50 people for any kind of multiple regression, but there is a rule of thumb that states that for every IV you have, you should have around 10 subjects. So you got 1, 2, 3. You got 2 IVs, so 10 times 2 is 20. So the sample size is plenty large, okay? So, again, I want you to read these things on Moodle. Each concept, each assumption, everything that you're going to need to know is on a Moodle page somewhere. So get used to reading these Moodle pages. Okay, back to your homework assignment. All right, moving on to question 3. You made a big boo-boo. The test of normality, the Kolmogorov-Smirnov test for normality, that is what we call univariate normality. That's when you first learn introductory statistics, where you start with a histogram to make sure that it's symmetrical and there's only one hump in the middle. That is what we call univariate normality. And unfortunately, regression models, that is not an assumption. Univariate normality is not an assumption for multiple regression models. Even though I've seen in other books that they think it is not. And I have a great example at these 2 web pages that I want you to read about normality. Again, univariate normality is not an assumption for any kind of correlation or regression model, but multivariate normality is. So the multivariate normality, I'm going to show you how to do that with a Mahalanobis Excel spreadsheet. It'll tell you if any of your subjects are too small or too extreme to be used in a study. Okay, but in order to run that, I have to run the test. So we're going to go ahead and run the test in SPSS. So hold on. All right, I transferred the data from the Excel into SPSS. I just named them IV1, IV2, DV. IV1 is the days outside the safety zone. IV2 is their scale of zombieism on a 1 through 5. And the DV is how many days they have left of being human. So we got to tell the computer what kind of variables these are. So the days outside is a scale, right? Because that's just a regular number. The scale of zombieism, we should probably put that in the ordinal. And days remaining human, again, that's just a scale, so that's good. Make sure you save your data a lot. I'm going to take a look at it to make sure we did get it in a right format. Yep. And I already forgot what the sample size was. 250? Was that what it was? Yeah, sample size 250. All right, so we can go ahead and run our multiple regression. You're going to want to analyze regression, linear. We assume it's linear. The DV is days remaining. These are your 2 IVs. We're sticking them in at the same time. So this type is called a simultaneous multiple regression, and you're going to learn about hierarchical and stepwise, but it has been my humble experience that it really doesn't matter which way you go. The results are always the same. So let's check these little boxes. Statistics, what do we want? We want the model fit. We want the R-squared change. We want all of these right here, okay? Click all those. Durbin-Watson, that's your autocorrelation, your independence of observation test. And so that's the good statistics plots. What we're going to do is we're going to check the residuals. That's your bottom, and your predicted is your x-axis, your residuals are your y. This will tell us about homoscedasticity. Save, this is a weird one. This is where the Mahalanobis check is. Okay, so all 3 of these will tell you if you have a multivariate outlier. And I'm just going to use the Mahalanobis because that's what I'm comfortable with. And you got to click OK down here. Options. Don't care about style. Click OK. Okay, this is going to give us the output, so hold on while I get it all straightened out. Here's the first output. So let's look up the Durbin-Watson number first. It should be somewhere between 1.5 and 2.5, depending on which book you read. So Durbin-Watson, here it is over here. Let me pull it over. So ours is 2.92, and that's pretty damn good. Let me see what you had. Good, you got the same thing. So it did not violate the autocorrelation, independence of observation. But now I'm going to go back up to the Multicollinearity. Okay, we're going to see if we have a multivariate outlier somewhere. So let's find our. This is our Multicollinearity distance. So according to this, our largest one in our data set is 12.565. I'll say that again. The largest Multicollinearity critical distance that we have, I'm sorry, not critical, but distance from our data is 12.5. So we're going to open up a Multicollinearity sheet. This will tell us what the maximum it could be, okay? So alpha is always the same. We don't change that. But n is our sample size, so that's 250. And k is the number of IVs we have, and we only have 2. And that's pretty much it. So there's the critical alpha. If we had any piece of data that had a Multicollinearity that was greater than 16.9, we should delete that piece of data. But the good news is we don't have any multivariate outliers. Okay, back to the exam. I'm sorry, back to the homework. All right, linearity, the assumption of linearity. You did something different. This looks more like a homogeneity of regression slopes. That's not used in this type of regression model. Okay, what number 5 is the linearity between each IV and the DV. There has to be a linear relationship. In other words, the correlation between each IV and the DV cannot be 0. So let's run those real quick in SPSS. The quickest way to do that is go to Graphs, Legacy. We want to go to Scatter Dot, Simple, Define. Our DV is remaining days. DV is always the y-axis, by the way. And so I'm gonna pick the first IV, put that as the y-axis. That's all I need. Let me click my OK button. It's down here. Sorry. Click OK. So there's the first scatter plot right there. Really can't tell what's going on. So you're going to double click on it, get the chart editor going. You're going to click on this little line right here. Bam, it's going to put a trend line in there. And if that line was flat, if that was horizontal, you'd be in trouble, but it's not. There is some kind of relationship going on, right? The R squared does not equal 0. So you have shown that there's a linear relationship between the first IV and the DV. We're going to repeat that with the second one. Hold on. Same thing, legacy, scatter, define. We're going to kick that one out and kick zombie scale in. Click OK. And here's our second graph. And same thing, you double click on it. You're going to put a trend line in there. And the same thing, it is not 0. R squared is not 0. So that's what I'm looking for with the linearity assumption. Again, it's the linearity between each IV and the DV. You got it? Good. All right, back to the questions. So homoscedasticity. What is homoscedasticity? That is that the distance of the residuals from the regression line should be relatively the same all over the place. Doesn't have to be perfect, but in other words, the spread of the residuals should be relatively the same across the entire regression line. And this looks pretty good. So how you do that is you go back to SPSS. Remember when we put that graph in there that said residual X, predictor X. So these are the residuals on this side here. And on the bottom, these are your predicted residuals. And this is the regression residuals. So what you do is you double click. Get to your chart editor. You're going to add a line. I forget which one. Oh, yeah, we need to add The lowest line, okay? Click on the lowest line. That's the one you need. Click apply, and then you can close it. And this should be relatively flat. It's not bad, okay? It's not perfect, but I do not think that it violated the assumption, okay? Because it's just got a minor crink in it. So again, the assumption of homoscedasticity of variance of the residuals was not violated. Next assumption, multicollinearity. Multicollinearity is when you have the relationship between two IVs that are practically identical. Say that again. When two IVs are highly correlated, how can you tell which of the IVs is affecting the DV? That's what multicollinearity is. And short version is you do not want two of your IVs to be correlated greater than 0.8. And to test multicollinearity, we either use the tolerance or the VIF. So I'm going to go ahead and look that up. It should already be on our SPSS output somewhere. So there it is right there. So tolerance, if this number was less than 0.01, you violate. And if the VIF is greater than 10, you violate. If you look at these things, they're inverses of each other. So you can use one or the other. You don't have to use both of them. But this did not violate the collinearity assumption. Good, you got that part. All right, trend analysis. You don't know how to answer that. That tells me that you did not look in the Moodle. Hold on. Right there, trend analysis. Bam, when you click that, it'll take you to this page. And let's take a look, all right? So we always assume that multiple regressions are linear data, okay? But there are other trends, right? Some data tend to fit a quadratic trend or a cubic trend, or there's all kinds of trends that are out there. We simply assume that it's linear, and the way to tell is to look on the APA output sheet. We go back to the lowest line, right? That's a general trend, okay? It looks pretty straight, so we're going to assume that this is linear. Next question. All right, was this a statistically significant regression? Right, you look at the ANOVA. So let's go look at our ANOVA. ANOVA, where are you? No, there's our ANOVA. And yeah, see, the significance is less than 0.05. Therefore, you did, in fact, make sure we got the right one, 10.678. Good, you did it right. Yes. So this is a significant regression. Next question. What was the effect size? Right. Then the effect size is simply R squared. Bam. That's 8%. And so you call it weak. It's not really weak. So the different effect sizes changes from test to test. But if you can get an effect size of 8% on a prediction model, a regression model, then it's actually pretty strong. Hold on, I got a table here. And of course it's in our modal, right? Go to effect size. So effect size for a multiple regression, we're using R squared. So if you had 0.08, that's actually a medium effect size, not a weak. That's a medium effect size, okay? So, all right, so you got a fair to good effect size. Now this thing right here, 28.2%, you quoted the R. The R doesn't work like that, okay? It does have some uses in other tests, but in multiple regression, we really don't care what the R states because you're dealing with more than one correlation. So that R is a combination of the correlations that we turned into the best fit line, that regression line. What we're really looking for is the R square. So that means that, 80.8, we can explain about 8% of the variance in the DV, depending on the IVs, that kind of stuff. So that's what we're saying here. All right, next question. We're both predictors significant, so let's go look at the coefficient table. There it is. Let me scooch it over. Scooch. All right, so there's your first IV. And the significance is less than 0.05. So yes, it's significant. Second IV, same thing. So they're both significant. Good. Perfect. You got those both right. Bam. Which one was stronger? Okay, so to test which one's stronger, we look at their beta weights, right? These are standardized weights. And the biggest one by far was their zombie scale-ism. Okay, so 0.194 is stronger than 0.154. So stages of zombieism. Good, got that right. This is where you should have probably put the B weight, the beta weight. Okay, so based on the regression, let me see what this looks like. So what this is this is the constant. That part's right. And right, you got this part right, and you got that part right. Good. This does look like the prediction equation based on the unstandardized B weights. Difference here is these units are different, right? Stages of zombieism, the units that we use there, some kind of scale, and the units here are days, right? So the scales are completely different. That's why we keep them as unstandardized. But again, the beta weights, they have no units. They're simply, this is the number of standard deviations. Okay. So far, so good. Let's look at your write-up. All right, your write-up looks pretty good. A few questions, though. You used Cook's distance instead of the Mahalanobis. Kind of curious why you did that. Again, why did you use the Cook's distance when we basically stick to the Mahalanobis around here? It's unimportant. You got the same results. And one minor thing, right? You said the assumption of homoscedasticity was violated, and I said it wasn't. So I think that this would make a fair prediction model when it comes to how many days a person has left as a zombie. So that's it in a nutshell. So I'm going to send you some links. I want you to watch this video, and I have another video where one of the tutors did the exact same data. She explains it a little bit differently than I do. But that's it. All right. MGZ out.